gas stoichiometry problems follow the same procedure as all of the other stoichiometry problems. However, these have the added properties of gases, and this is a typical example of a gas stoichiometry problem. Methane gas with a volume of 2.8 liters at 25 degrees Celsius and 1.65 atmospheres is mixed with oxygen gas having a volume of 35 liters at 31 degrees Celsius and 1.25 atmospheres. The mixture is ignited to form carbon dioxide and water. Calculate the volume of CO2 formed at 2.5 atmospheres and 125 degrees Celsius. And the balanced equation is written below. So typically in previous stoichiometry problems I'd have moles or I'd have grams, and then I'd try to find the amount of grams formed of a product. But here I have a gas. Gas has pressure, liters, temperature, all of these other things from the ideal gas law. So while I can have a typical stoichiometry problem where I just look for grams, but what is going to distinguish these problems from the rest of them is cases where I'm looking for pressure, volume, temperature, other sorts of things using the properties of gases. So let me go ahead and begin solving this problem. This should explain itself. It's not any different from any other problems, except I'll be using things like the ideal gas law to find moles or to find some other property of gases. So the first thing I need to do is figure out how many moles of my product I'm going to get, because information is given to me about the reactants, but in this problem I'm looking for the volume of carbon dioxide formed. And here the first thing I need to do is figure out how many moles of methane and oxygen I have, so I can figure out how many moles of carbon dioxide I have. Now I'm not given moles, but I am given liters, degrees Celsius, and atmospheres. So with this information I can figure out the number of moles of each of these reactants, methane and oxygen, because I will have 3 out of 4 variables of this equation. So let me begin by finding the moles of methane and oxygen. I'll begin with methane. I'm going to be using the ideal gas law. PV is equal to nRT. And I'm just going to begin filling in the formula and just solve for the number of moles. Methane was at 1.65 atmospheres. It had a volume of 2.80 liters. Moles are the variable I'm looking for. R is the ideal gas constant. And it was at 25 degrees Kelvin, which I must convert to, or at 25 degrees Celsius, which I must convert to Kelvin. 25 plus 273 is 298. And now I just solve for n. It's a simple algebra problem, and n ends up being 1.89, or 0.189. That looks like a 9. Now that I have that, now I need to find the moles of oxygen, and then after that I'll look for which one is the limiting reactant. Moles of oxygen, this one was at 1.25 atmospheres, 35.0 liters. and it was at 31 degrees. Yeah, 31 degrees Kelvin or Celsius. I hate it when they put stuff in Celsius. Whatever. It's just more tedious, mindless work to do. 304 degrees Kelvin. Solve for N. This is going to be equal to 1.75 moles. Oxygen. Now I need to figure out which one of the reactants is the limiting reactant here. It's pretty obvious from this equation. It takes 2 moles of oxygen to react 1 CH4, but I have so much more oxygen. It's very obvious which one it's going to be. It's obviously going to be CH4. But anyways, we'll do it the old-fashioned way. 0.189 moles of CH4. 1 mole of CH4 reacts with 2 moles of oxygen. And this is going to give 0.78 moles. Or 0.378. So oxygen. This is how much oxygen would be required to completely react all of this CH4. I have 1.75 moles of oxygen, which is way in excess. It was very obvious from the beginning. So oxygen is going to be in excess. CH4 is going to be the limiting reactant. So now that I know that this is limiting, I'll go back to my original equation. I'm looking for carbon dioxide. CH4, 1 mole of CH4 gives 1 mole of carbon dioxide for products. So that means I'm going to have 0.189 moles of carbon dioxide. And I'm looking for the volume, and I'm given that it's at 2.50 atmospheres and 125 degrees Celsius. And now I have moles. So all I need is volume. I can simply use the ideal gas law one more time and get the final answer. So pressure is 2.50 atmospheres. Volume is what I'm looking for. N is 0.189 moles. Ideal gas constant is always the same. Unless it's in different units. And 125 is 398 Kelvin. To solve for V, V is equal to 2.47 liters. So this is all I need to do for gas stoichiometry problems. It's very similar to regular stoichiometry problems, except what distinguishes these ones from regular stoichiometry problems is that I'm using my ideal gas law to get the moles, and after I have what I would from a regular stoichiometry problem, if I'm looking for a different property that is only specific to gases, then I would use the ideal gas law. Basically, a gas stoichiometry problem is any stoichiometry problem where I have to use the ideal gas law or something similar.